Today we continue to work on our tower blocks game, and the goal of this episode is to add custom lighting using OpenGL shaders. To achieve that goal, we are going to be using this amazing learnopengl.com resource, which has very nice articles describing how the basic lighting works. Mostly today's shaders will be based on the basic lighting article and the materials one. I suggest you to read about it, explore yourself. Everything is described, explained the way that you can understand, and then you won't have any troubles following me when we implement things for our scene. So as you remember, right now we're drawing the cubes with predefined color, and then we rely on this draw wires to make sure that the cubes are distinguishable, or the blocks, not the cubes. And we would like to avoid drawing the wires because they don't really look that nice. Sometimes they are bold, sometimes they're very thin. If you make a screenshot, you will see that the wire is like dotted and so on. So let's get started right away. And first thing that we need to do is we need to load the shaders that we're going to work with. So for our game struct, we will define lighting shader. And in our init game, we can then say that lighting shader is load shader, a very nice helper function from Raylib that knows how to load both vertex and fragment shaders. So we'll create a directory named shaders, and we will have lighting vertex GLSL and shaders lighting fragment GLSL. If we run our program now, it's loaded and runs, but there is a warning saying that, hey, there is no such file. That's why we need to create the shaders directory, and then we can touch lighting vertex GLSL and lighting fragment GLSL. Let's jump into vertex first. I'm going to be using 330, so like modern OpenGL void main, and we need to set the GL position, the global variable, to our position of the vertex. What we will have is MVP matrix, so model view projection matrix times vertex position, and MVP is matrix 4x4. This one is provided by Raylib, and vertex is vec3 vertex position, and it's also provided by Raylib. So what we need to do here is actually convert it to vec4. Now, how do I know that this is provided by Raylib itself, and what kind of things does it provide for you to know? There's this custom shaders on wiki, and it tells you all about the default attributes and uniforms that Raylib tries to provide for your shaders. So that's where we get our vertex position and MVP, model view projection matrix. It can also provide you the matrices one by one, the view, the projection, the model, can provide you normals, some colors and other things that you might need. For now, all we need is just model view projection matrix in the vertex position so that we can put it into our view. And for fragment, we will make it even easier than before. We need to say that we're gonna produce a frag color, which is going to be vec4, and we can say that output is simply white, right? So 111 in RGB with alpha set to 1. This should result in white color. When we run our game, nothing really is affected, but what we're interested in is this logging, which says that everything compiled correctly. So our shader is now loaded, and we can actually use that. And we have this nice function, draw block. Here we're drawing the cube, and we are drawing the wires. During the draw cube call, it uses the default vertex and fragment shaders, which Raylib provides on its own. And we can actually use different shaders, saying that, hey, there is a begin, what was it, shader mode, I think. Yeah, I think it's begin shader mode, some lighting shader, then we can say end shader mode. We need to pass lighting shader to this function, and then fix the places where we call that lighting shader. Let's run our game again, and we can see that it's working. Basically, we are now quite confident that both vertex and fragment shaders work correctly. It outputs our white color, and for falling blocks we have different calls. We have different function which doesn't currently use this shader, and we will fix that later on. For now, we're really interested in adding the lighting. And as the articles in this Learn OpenGL resource tell us, for basic lighting, we really need to achieve this like Phong lighting effect. We need the ambient light, diffuse light, and specular light. And then there is the article about materials. So the material of the block can define the ambient, diffuse, and specular properties, and then the light itself can also be defined as these three different values. This way you can manipulate the materials, how they reflect things, and the lights themselves, because the lighting can also be different. So the first thing that we need to do is we need to work on our ambient light. So I will define a block for light properties, so light ambient, and below there will be a block for our blocks, so block ambient. These values you can really like play with, but for our light I'll tell that, hey, like the light ambient produces the full 100% values, but the block itself will be only like 40% to reflect that ambient value of our light source. Then we can say that ambient is nothing but light ambient multiplied by block ambient, and the frag color then becomes block color times ambient. We don't have block color yet. It should come into this fragment shader, and we can set it up as uniform block color. So this should be it for to add ambient lighting, but we don't have the block color yet. If we run it, everything's black. That is because our block color is just a pack of zeros. Let's fix it first in our draw block. Before we drawing the cube, we need to invoke set shader value. So for our lighting shader, we can get the location of block color uniform and set some vector3 value based on uniform vec3. Now we do have block color, right? Because we keep track of each block's color itself, but the color struct here is actually keeping those values in the range from 0 to 255. And what we would like to get is normalized colors, so in range from 0 to 1. That is exactly what color normalize does. We can then say that vector4 normalized color is this, and simply provide normalized color x, y, and z components. Let's see how that affects our rendering. And now we can see those darkened blocks. Why are they darkened? That is exactly what this 40% block ambient does. So even though light produces like 100%, it affects 100% of its light, gives towards the lighting. The block only reflects like 40% of the ambient color. We can actually drop ambient for a bit to show you that if there was no ambient, then it would look like something like this, same as before when we drew blocks without the wires. Now, ambient itself doesn't produce any interesting results, and we need to start working on the diffuse part. So diffuse lighting pretty much tells you that given some light source, given some vertex, and it's normal, we can calculate the how much this light direction and normal direction, how much they align. If they are aligned perfectly, then you get like 100% impact, and the smaller the alignment, the less the alignment, the smaller the value is. That's where we have the dot product. So if we know the direction from this point towards the light, if we know the direction of normal, which is also normalized, right? Dot product gives us that specific value from 0 to 1. Of course, we're dropping the values which are negative, so dot product can give you from -1 to 1. We're not interested in anything below 0. And it can tell us how much light it can contribute. So let's do just that. Pretty much what we're interested in is, first of all, we need some light position, right? So there should be some light. We can define it as something like -50, 500, -50. So these values are not random. If you remember, in our main, when we set up the camera, it's actually in position 50, 50, 50, and then the Y grows as the blocks are being piled up, but the X and Z remain the same, and we're setting -50 and -50 so that when we reach specular lighting, it actually has a better effect, because the angle at which we look at the blocks is actually going to help us to be reflected directly at the light source. Other than that, it's like pretty high. We're setting it like in the sky, let's say. So that's our light source. Next, we need to define the diffuse parts for light. Once again, 100% is going to contribute to diffuse lighting for the light source. And for the block diffuse, we can say that, hey, let's only do 50%. All right, so we have this diff value, which is dot product between what? Between our frag normal and minus light direction. So light direction is going to be from light towards the frag position itself, right? And minus is going to be reversed, so it's going to be from frag position towards the light. And this is our normal. Dot product returning the values from -1 to 1. So we need to clamp it to 0 to 1, or pretty much turn every single negative result of dot product into 0. So not really clamping. Or maybe it is, if you think about it. Yeah. And then our diffuse part of our lighting is going to be diff times light diffuse times block diffuse. And then we can sum these parts up before multiplying it by block color. So what we're missing? We're missing the frag normal, we're missing light direction. So what is light direction? Light direction is normalized vector. So what we want is from here up to here. That means frag position minus light position. Frag position minus light position. And yet again, another variable that we don't currently have value of, frag position. So what we're interested in is we need to get them from somewhere. Frag position and frag normal. And we can get them from our vertex shader. So vertex shader should tell us that, hey, I'm going to produce those frag position and frag normal. So it's going to be like frag position something and frag normal. We already have vertex position, and I think the frag position is all about world view, right? So where it ends up in the world. So we need to say that this is going to be model matrix times vec4 vertex position 1 0, and because it's vec3 we only need 3 components from that. Mat model is another uniform provided to us by Raylib, as I showed you before, same as MVP. And for frag normal, we can first set it to vertex normal. Vertex normal is again yet another value provided to us by Raylib. Okay, let's see what it does. It says that, yeah, we made some mistakes. Frag position, frag normal. We get frag position, frag normal, light position. Some sort of mistake was made somewhere. What does it say again? Failed to compile, normalized. Okay, yeah, it should be normalized. Right? And we get a really nice result. We can already see shades because the light is somewhere like on top. So the sides of our block, they get some shading. And the ambient light actually helps to keep those sides as a somewhat darkened color, not entirely black. What we see here is nice shading, nice lighting, but the falling blocks are still being drawn the old way. Before we jump into the falling block section, let's fix 2 things first. For vertex, this article tells us that in case some non-uniform transformations happen, the normal actually changes and we need to recalculate the normal. So instead of just providing the vertex normal as it is, we can say that we can grab our mat model, we can inverse it, we can transpose it, then we can probably do the mat3 from it times vertex normal, and then we can normalize it as well. So this is exactly what this article tells you about. You can probably search about why it works, how it does it. For even I myself haven't researched it that deep to understand how we end up with this kind of formula, but as long as it works, fine by me, except that I made a mistake. Transpose should be transpose. Everything remains the same because we don't really have those non-uniform transformations. Let's get back to our fragment shader and work on the last part, the light specular part. This time the light source will only provide 50% of its light towards, it's going to contribute only 50% of its color towards the specular property, and the block specular, let's do like 100%. So this is like the material. You can change these values, right, and they will be shown differently using the same light source. That's how you can mimic like iron, gold, plastic, rubber, and then there are different lights which can actually produce different lighting. So the things that we need for specular lighting is what? We have the same light source, we have the same normal, but now we have this eye or camera. This is the place from which we look, and pretty much if our camera is, for example, on this tip of orange vector, and this vector R is actually reflected I vector, or not I, the light vector. This is like light direction from here to here. It gets reflected by this N, which is perpendicular. And if we as a camera are on this tip, it means that our reflection looks directly at this light. And then if our camera diverges from this position, either towards the top, towards the bottom, it means it has less and less contribution to the specular lighting. Pretty much we would like to see something like a white spot when we are at this position, and lesser and lesser brightened spot as we go down or up. So think of it like if you're looking in the mirror and you see the light, it's like really bright, but you can look from different position at some particular spot, and if it doesn't reflect the light, it still gets highlighted, but not as much. It gives you all the calculations that you need to do. Again, the same dot product. There is now view direction, which we need camera position for. There is this reflect direction, and then there is this shininess parameter, which tells you about the effect that you get. The higher this shininess parameter, the more localized this specular spot is. We're going to use 32, same as the article describes. So let's think about it. So spec is going to be something 32 maximum of dot 0. Dot is going to be between view direction and reflect direction. Right? This is the same as in an article. Then our specular component is going to be spec times light specular times block specular. Then we can add it to our color, final color. And let's think. We have this view direction and reflect direction. Let's start with reflect direction, which is as easy as using reflect function, where we have light direction vector and our frag normal. Right, so that what it does is that we give it the normalized vector from light towards the frag position. We can give it the normal, and it produces us this vector from frag position towards our camera or whatever. Just it gets reflected. And view direction is normalized. What we need, view direction, it has to be from frag position towards the camera. So camera position minus frag position. Then we need to have this vec3 camera position to come from our C code. because our camera constantly moves. And this should probably be it, right? So if we run it, first we check that shader compiled successfully. We can see this artifact right here in the middle when the block moves. This is because our camera position is somewhere at 0, 0, 0, right? Because we don't pass it as uniform, it defaults to zeros. It kind of affects the specular lighting a bit, but not much. So if we jump to our main function, our camera position gets updated here, update camera position, and we can then set the shader value of game lighting shader, get shader location for camera position uniform. The value is camera position, uniform type is our vec3. Running our game, let's see. No, actually we won't see anything because specular lighting doesn't happen for us, and it will be seen on the falling blocks. So we need to actually go into the draw falling blocks and apply the same thing as we did before. We have draw model called, draw model wires. We're dropping the wires. We can say begin shader mode, game lighting shader, and shader mode. And I think that we need also to grab the colors as well. Game lighting shader, fix everything. So once again, we have the color, we normalize it, pass it to our shader as block color uniform, enable the shader, draw the model, run the program, and our falling block doesn't have any shading whatsoever, even like it has no lighting. And that is the difference in Raylib. So the difference between draw model and all the draw primitives like draw cube or draw sphere, right? So these primitives that Raylib provides to you, they are actually affected by this begin shader mode call. But for draw model, the shader to be used resides in game cube model in materials, right? And there is this shader property which we can then set to lighting shader. This way, when we are invoking draw model, it will actually grab the shader from the materials. Let's run it again, and you can see that the falling block is now correctly shaded and the specular lighting works as well. That is looking much better than before. So that is pretty much it for this episode. For the next episode, we will probably start working or try to work on the extra stage. So right now we are at game over, and if we press a button, press this space or click, we are instantly at the playing state. What we would like to do is to add another stage. So once the game is over and we're clicking or pressing the spacebar, we have like half a second animation where the blocks disappear in some sort of animated fashion, and once it is complete, we are happy to proceed with playing the game again. And finally, as has been requested in one of the comments to the videos, to this series, is to add some sounds. I will try to search for some free to use sounds and add them to the game. Hopefully will result in another small tiny episode. But for today, that is pretty much it. Hope you enjoyed the video. Please press that like button, and if you haven't, please do subscribe to my channel, helps me greatly. Thank you. I'll see you again. Bye.